This week, the wide world of 360 video, the artistic world of Marina Abramovich, and the strange world of quantum computers. Imagine a computer that could crack the world's most secure codes in minutes, design extraordinary new medicines, even pave the way to intelligent machines. Big tech companies like Google, IBM, and Microsoft are all trying to be the first to achieve a breakthrough in the field of quantum computing. But, well, we're not quite there yet. At the moment, if you want a quantum computer, you need all of this. You need your ionizing lasers, your cooling lasers, and your processor. You need all of this, and currently, all this can do is add a 0 and a 1. But it does do it in a really cool way. Quantum computers harness weird and wonderful phenomena seen only at very small scales. The data in an ordinary computer is represented as bits, each of which can either be 0 or 1. A quantum computer instead uses quantum bits, or qubits. Now these qubits can be both 0 and 1 at the same time. This is called superposition, and it's a key feature of a quantum computer's unique powers. So, when a quantum computer adds a 0 and a 1, it's also adding a 1 and a 0, and a 1 and a 1, and a 0 and a 0, all at the same time. So, number crunching could, in theory, be done much faster on a quantum computer.
There are a few really important things that we know they will be able to do if we can ever build them. So one thing is searching through a database. Let's say you've got a list of about 1 million items, say, and you want to find one particular item through that list. Well, all an ordinary computer can do is look through that list one item at a time. Look at the first item, the second item, the third item, until eventually you find the item that you're looking for. A quantum computer can, in some sense, look at all those items simultaneously. We know that quantum computers will be able to help artificial intelligences learn better, learn faster, optimizing things, designing things. If you're trying to design, let's say, the shape of a car so that air will flow over it in exactly the right way, that's an optimization problem. It looks like quantum computers are going to be extremely good at that.
And then there's code breaking. If you give an ordinary computer a code to break, it will try every possible combination one at a time. But give a quantum computer a code to break, and it can try all the codes at once.
This is a huge area of application of quantum computers, and it's really financially the driving force in putting money into the industry and persuading people to really try to build these things. The first government which has a functional quantum computer which can break into secret messages is going to be at a big advantage, and maybe we want to try and hide away the fact that they've got those capabilities.
And if superposition wasn't weird enough, a quantum computer's qubits can be paired up or entangled, and then can instantaneously affect each other from anywhere else in the universe. Well, that's all very well in theory, but it is really hard in practice. At Sussex University, researchers are preparing for the challenge of scaling up their prototype quantum computers to take them from handfuls of qubits on the lab bench to industrial scale.
So what you see here is an actual working quantum computer. As we're filming this, you can literally see an atom, for example, be in one state and another state simultaneously. And what you see on the screen is the evidence that that really occurs, that you really, the atoms are in this very, very strange and counterintuitive state. So quantum computers have been in a way for a long, long time the holy grail of science, and with that it actually seemed nearly impossible to build them, and so people felt maybe it's just never possible to build such a machine. The reason why it's so hard, because to control quantum effects in such a way allowing us to build a large-scale quantum computer is tremendously hard. Quantum effects, like that an atom can be at two different places at the same time, or entanglement, what Einstein referred to as spooky, these are just so hard to control.
At the moment, these prototypes offer a glimpse of how these computers might work in the future. But how will we use them when we have them? What does a quantum computer program look like?
The basic building blocks of a quantum computer program are really very alien to us. They're things like superposition and entanglement. Those are the right high-level concepts to be to put into our quantum computer programs, but it's very hard for the human brain to understand what entanglement is and what its consequences are. Thinking of qubits as connected by pieces of string actually works extremely well to help us design and design our quantum programs and predict what they will do. So perhaps a high-level quantum programming language of the future could look like could look like a knot, or could look like a children's game of untangling the fishing lines and see who's got which fish. You could imagine drawing all these strings and having them connected to each other and going up and going down and coiled around, and the pattern of how those strings interact, that pattern is your quantum program.
I do feel the programmers have a little bit of time to sort their software out though, because the hardware is also still a work in progress. I've gone underground to see Oxford University's quantum computer. The lab is a wizard's paradise of lasers, vacuum chambers and traps for atom-sized particles. It's an ion trap. In the lab, they've achieved a world record level of control over their quantum bits. They can even show off by making a single qubit glow in Morse code. C, L, I, C, K. Click. What will your quantum computer look like? It won't be this size then?
So ideally it looks incredibly boring and incredibly small. Okay. So when we build something like this, it takes an optics table. So this is 2 meters by 1 meter. By 1 meter high. We think we can get this down to something the size of a shoebox in the next 5 years.
Once you've got everything in the right place.
Once we have everything in the right place, machined down, optimized, and rather than made by physicists, made by engineers. Right. To make something that actually works rather than has enough knobs on that when you have enough people twisting them, they do something right once.
You're not looking to put more and more qubits into the same box, are you?
What we want to do is build devices that can contain about 5 or 10 qubits. We'll build many of these devices and hook them together via a network. So this is the same way as if you have a supercomputer. Nowadays you don't have one big computer. You have lots of smaller computers that hook together in a data center. You see these data centers thrumming with lots and lots of different machines and lots of blinking lights. That's what we envisage these things are.
It does sound like it's not the most efficient design if you're plugging lots of these things together with optic fiber, rather than making a quantum computer that has 50 qubits in one place.
Yeah, the most efficient device we could ever build would have all the qubits being able to talk to every other qubit. And that's really, where ideally you'd want to be. But you'll always get to the point where you can't put any more qubits in your device, where you build a device that's so big you can't build a bigger one. And at that point, what we want to do is have a network we can build up. So once you've got as big as you can with these techniques, you can then network them together to build bigger networks.
The huge potential of quantum computing has attracted big tech players. Google told us it will have something big to announce in March 2018. IBM has a 20-qubit quantum computer that researchers can program over the internet. Both these companies are trying to build reliable quantum computers of around 50 qubits. Now, at this point, they will achieve something called quantum supremacy, which sounds world-changing, but it might not be.
Why I don't like the phrase is that when you cross that boundary, nothing instantaneously magical happens. It's just the point at which you can't predict what the machine would do. It's the point that the machine might be useful for something, but to be honest, we haven't worked out anything that a, say, 60-qubit quantum computer could usefully do. So it's into the uncharted territory, very exciting, but it's not the point at which the quantum hardware is supreme. You should not throw away your iPhone or your desktop computer or even your supercomputer and have a quantum computer instead.
So with more tech companies getting serious about quantum computing, there is now a place for them to show off their ideas. It is the Quantum Technologies Fair in London, and Kat Hawkins has been along to see what is on the quantum horizon.
When it comes to quantum computing, a lot of the research still seems to be happening very much in academia, but I wanted to find out how much of it is being taken away from the lab bench for applications in the real world.
Every stall at this fair is using the same tech used in quantum computing. The principles of trapping, manipulating, and measuring tiny atom-sized particles. But the practical applications here are creative and potentially life-changing, from diamonds used in heart disease sensing to capturing individual virus particles.
They're really designed to be able to measure very, very sensitively at very, very small length scales. So it's ideal for things like nanoparticles, like viruses, and indeed for measuring chemical signatures as well. Use the mouse to move that scale bar back and forth. It should be fairly obvious when it flashes really bright. There you go, that's it, that's it. When it wiggles around, that's when you've got a particle trapped in your resonator.
The ultimate aim is that viruses could be picked up using this diagnostic tool, but the main focus now for most people here is on overcoming the engineering challenge of making large, bulky systems a lot smaller.
Heavy industry, all the way through to defence and security, transport, and then healthcare technologies. It's incredible to see how many stalls here are researching so many different areas when it comes to quantum technology.
And they're all working together with an open source mentality, along with a lot of investment. The British government spent £270 million over the last 5 years on quantum technology research.
The collaborative element, especially the number of things that NPL is involved in, because we have a lot of the core technology and science, and we're just looking, what are the actual applications in the UK business world?
From afar, a lot of the applications here still look like complex machinery. But Anne Curtis has been looking into its potentials in an important area, far, far away.
So one of the main applications we can use for quantum technologies is quantum sensors. And what we're doing in this experiment is we want to sense greenhouse gases and measure how much there is, how that's changing over time. And one good way to monitor large-scale systems is from space. To put something properly on a satellite, it has to go through all the space qualifying tests. So every item in there would have to be space qualified. Most of the fiber technology isn't so good in space due to radiation effects, but there's no reason why this couldn't be miniaturized and put up in space. It's just the next stage of funding.
It's so hard to be here today and not feel excited about quantum technologies. But one thing everybody has said to me is that their particular real-world applications are a few years in the future still. So when it comes to quantum computing, it's still very much a case of watch this space.
Hello and welcome to the Week in Tech. It was the week that the Federal Communications Commission in America voted to repeal rules on net neutrality, which had stopped internet service providers from offering different speeds and priorities for traffic online. The extraordinarily elongated interstellar asteroid Oumuamua was being checked for signs of alien technology, and here on Earth, the faces of 2 billion people can be compared in a matter of seconds, with the Minority Report style system Dragonfly Eye unveiled in China. It was also the week that Netflix was caught up in a creepy viewing controversy. After revealing on Twitter that 53 subscribers watched the holiday film, A Christmas Prince, every day for 18 days in a row, Netflix defended the tweet, saying it represented overall trends and not specific individuals. The city of San Francisco has banned the use of delivery robots on most of its sidewalks, stating, "Not all innovation is all that great for society." Meanwhile, Dutch police say it may not have been such a good idea to use eagles to catch drones after all. Who could have guessed? Seen here on Click, the birds were trained to snatch the machines from the sky, but the cost of keeping the eagles was too high for too low a demand, and they didn't always do what they were told. And finally, if you're missing Harry Potter, don't despair. Artificial intelligence may have a solution for you. A new chapter has been created for a book called Harry Potter and What Looked Like a Portrait of a Large Pile of Ash. Its plot twists include Harry dipping Hermione in hot sauce and Ron turning into spiders and trying to eat Hermione's family wizard.
Now, earlier in the year, we looked at some of the 360 cameras that had taken off in 2017. Dan filmed with the new kid on the block, the Insta-1, in Berlin, and he came back very pleased with it. Easy to use, lots of features, including this bullet time mode, a bit like in the film The Matrix, where you can get a picture of yourself from all angles. But what have the more established names in photography got to offer us? Well, with Christmas just around the corner, this time we sent Dan to a suitably festive place to put two prosumer 360 cams through their paces.
The ancient city of Bath hosts a very traditional Christmas market, one that I want to catch in the round. I've got two cameras for the job. One's from Kodak, the other is Nikon's. They look pretty similar, with two ultra-wide-angle lenses capturing everything before the two images are stitched together in camera. But look closer and you'll see the Kodak sporting two different lenses, one smaller than the other super wide 235-degree lens. It's also got the tiniest remote control in the world and a slightly higher price tag than the Nikon. Our producer Mehnaz has the Kodak while I'm putting the Nikon through its paces.
Now, we don't just want to test these cameras out in the daylight when all the conditions are absolutely perfect. For these cameras, we want to test them out to see what they're like as it starts to get dark. Will the bright lights be a problem, and will we see all of the detail?
Time to go for a wander and see whose 360 is best.
Please dive in, ladies. Don't let me get in your way.
And in no time at all, I found the festive liquor stand. Not just wine, but flavoured vodkas here. And the Nikon's not put off by those flashing lights. But the image is a little dark, so we'll brighten it for you in post. There we go. And now you can see the other problem. The image stitching means I've almost lost my head before touching a drop. The Kodak's picture is brighter than the Nikon's, but we found that the quality from that super wide-angle lens was softer than the smaller lens it houses on the other side of the device. Of course, you're best off with a stick attached to both of these cams, otherwise your hands get sort of in the way. Now, to make the test fairer, we decided to see how these cams fared back to back, or front to front, or back to front. Well, it's difficult to tell, to be honest. We shot them side by side.
Look at this, we found a 360 globe for a 360 camera.
And it's the Nikon showing off more natural colours, benefiting from a more accurate white balance, although some might prefer the warmer Kodak results, as it's very Christmassy. At the chilly cider shop, again, Kodak warmed things up, while Nikon kept things more natural and crisp. Both cameras struggled to perfectly stitch their two shots together. This is the raw footage with no touching up, and the Nikon's done a reasonable job. The stitching point is more visible on the Kodak, partly because of the different qualities of those two lenses. On the upside, it's Kodak that offers the ability to play with how the images are stitched together in its free software, something the Nikon's more basic offering lacks. For sheer fun, the Kodak also offers greater flexibility when playing back what you've shot. This is Little Planet mode, and if you want to do it on the Nikon, then you'll need some third-party 360 software, which may mean additional cost. Finally, the thing that everyone forgets when they use a camera, sound.
It's very odd being filmed by two cameras.
Isn't it? We're being filmed as well, because it's 360.
Oh my god.
I know.
Goodness me.
You can tell that she's had a bit too much cider, because hers moves around a bit.
No, I'm just cold.
We reckon both do a great job, but the Nikon is slightly clearer, although the Kodak offers the possibility of attaching an external mic. So which camera will enthusiasts be hoping Santa brings them this year? We think the Kodak edges it for easier post-production, while the Nikon has a better shot. But if you're hoping for a trouble-free, cinematic, seamless result for under £400, you may have to wait until something else takes off. At least for now.
This is Acute Art, a virtual reality arts platform and a gallery without walls. And it's about to launch with VR works by some of the world's leading contemporary artists. Amongst these works is one by Marina Abramović, the self-confessed grandmother of performance art, who pushes her own body to the limits as a vehicle to challenge and move people. Right, there we go. Okay, well there's Marina in a tank of water. Well, she seems to want to talk to me, but the water is rising up her body.
In real life, when someone rescues another person or offers aid of any kind, there is a transfer of energy. Approach the water.
I think she wants me to touch the glass.
Make contact with...
Oh, okay, right. Now I'm somewhere very cold and everything seems to be going wrong. As always with VR, you really get a sense of scale. I mean, that ice shelf looks absolutely enormous and it's crashing down right in front of me. This work is an expression of Marina's fear that humans will not survive the consequences of climate change if we don't change our behaviour. I'm being covered in spray. And now there's a note.
I will walk instead of drive. I will reuse what I can. I will reduce the waste I create.
Marina wants to leave the participants with the feeling that they should do something good for the planet.
We have to save this planet that we are living in, because what I'm interested in is to create the literally contract with the, with the planet Earth, and give my word of honor that I will do something to save.
You are pretty well known for pushing your body further than most people would want to push their bodies. Here you appear virtually in a tank of water, but I get the sense that you still did some pretty real stuff to make it seem as real as possible.
Actually to do this, I have to really be in the water, and then we have to really be in the swimming pool and with the two divers holding my legs, that I can really go in and sink and feel what means floating and what means actually dying if you don't have any more air to breathe. So it's funny that you have to do something which is virtual, but you still have to do physically.
Before, you've said that you don't think your performances can be captured adequately with photos or video because you need to be there. You need the experience is actually physically being there. And I wonder whether virtual reality is close enough to being there. That's why you chose it, because it's kind of almost being there, isn't it?
It's very important, that kind of energy dialogue between the audience and the performer. And the only the thing can catch, before it was just video, because it can catch sound and movements. Virtual reality is really another step further, because you can go around the objects, you can interact, you can do this. But still, I think that's so much question of how much energy and charisma actually can be transmitted from the real performance into the virtual body.
The rather mesmerising Marina Abramović. And we'll hear more from Marina in next week's programme, which is the Christmas show. So expect tons of sensible journalism and no fun whatsoever. Maybe. In the meantime, you can follow us on Facebook and on Twitter, where we live at BBC Click. Thanks for watching, and we will see you next week for Christmas.